Good afternoon or evening, or time appropriate greetings to wherever you are. It is Philosophy Roulette time, number 58. And here we are at Phil Papers. We are going to find some philosophy to read. Cool. See what's new. We looked at some of this morning. Let's see. We looked at some of this. Foundations of Physics. I don't know if I can actually read this because of the number of formulas that were probably in it, but we can I want to take a gander at it at the moment. Confessions of a Cheap, Sophisticated Substantivalist. Well, I'm cheap. Heck, I do this for free. Sort of amazing. The whole argument, homotopy type theory. Well, James Ladyman and Stuart Presnell. You know, I mean, Ladyman's a little bit famous. It'd be like, let's see. How long is this actually? 10 pages in Philosophy of Physics on the whole argument. Now, there is a whole argument. Oh man, I haven't thought about the whole argument in like 15 years, maybe more. Yeah, like 20 years. Alright, let me just go. Let's just take a gander at how many formulas there really are. Yeah, see, here's the real problem. If you get too many formulas, then it's just like you have to understand the math, and I can't explain the math, even if assuming I even know what the heck is going on. You know what? This doesn't look any worse than any of the other ones, really. You know what? So, shoot, we're gonna do it. I don't know. It's not that long. We'll give it a shot. If you're ever in the live chat, you can always type !paper, and then this link will pop up and you can follow along if you so choose. Okay, the whole argument is primarily about the meaning of general covariance and general relativity. As such, it raises many deep issues about identity in mathematics and physics, the ontology of space-time. See, we're drinking Corona today because my dad has a sense of humor. And he bought me the beer. And ontology of space-time and how scientific representation works. This paper is about the application of a new foundational program in mathematics, namely homotopy type theory, HOT, to the whole argument. Homotopy type theory. I should probably say that. I'm not even sure how to say that anymore. I used to know. It is argued that the framework of HOT provides a natural resolution of the whole argument. The role of the univalence axiom in the treatment of the whole argument in HOT is clarified. Okay, the HOT framework provides natural resolution. Okay, Einstein said that the general laws of nature are to be expressed by equations which hold good for all systems of coordinates, generally covariant. This does not mean that the laws of physics take the same form in all coordinate systems, although that remains a common and not unreasonable rough formulation. See, for example, Dainton, because, for example, is it me or is there double parentheses here? Okay, this is just, okay. There's a, okay, reference. Because, for example, classical electromagnetism can be formulated in a generally covariant way. Very briefly, dF equals 0 and d star f equals j, where f is the Maxwell-Faraday tensor representing the electromagnetic field, and j is the forecurrent that represents the charge density and current density. Okay, whatever. But the familiar Maxwell equations are only recovered in inertial coordinate systems. Yeah, so laws of physics work everywhere all the time is kind of like the rough thing, but the very specific ones that make sense to us the familiar ways that the way that the physics looks in the familiar way only happens under certain conditions. And that's inertial coordinate systems. Rather, general covariance means the equations of the theory are formulated in a way that is independent of coordinate systems, as is the language of the tensor calculus. Yeah, the science works everywhere, but for it to look in the convenient way to us, it has to be under certain conditions, but that's independent of coordinate systems, is the law themselves. General relativity was the first theory to be formulated in a generally covariant way. The theory is defined by the Einstein field equation as follows, in units chosen such that the gravitational constant and the speed of light are both 1 and without the cosmological constant. Okay, so formula. Models of general relativity are Lorentzian manifolds with metric and stress energy fields defined on them, and that together satisfy this equation, and so dropping the indices, they are of the form mgt. If there are electromagnetic fields or other fields, then they contribute to the T, but models of general relativity often involve only gravitational matter or may have no matter at all. Yeah, so they're simplified to talk about what they want to talk about. The maps that transform between coordinate systems defined on differential manifolds are diffeomorphisms. Ooh, fun word. Diffeomorphism is a smooth that is infinitely differentiable transformation between manifolds that has a smooth inverse. Diffeomorphisms on manifolds induce mappings on the geometric objects defined on the manifold, the metric and the matter fields. A diffeomorphism H from M to M prime lifts to give an isometry mg to m prime h star g. H star is automatically defined for any other field on M. Any two models of general relativity that are related by diffeomorphism are empirically equivalent. So basically, you can transform one model into another, as long as you got this sort of smooth thing, this smooth diffeomorphism. Okay, in the sense that all equations about measurable physical quantities have the same answer in any two models that are related by diffeomorphism. In the case where m prime equals m, the diffeomorphism group partitions the set of solutions into equivalence classes, where two equivalent mode models have the same observable properties. The set of solutions is closed under diffeomorphisms, meaning that for any h and any mgt that is a model, m h star g h star t is also a model. While theories other than general relativity can be given a generally covariant formulation, their sets of solutions are not closed under the action of the diffeomorphism group. Solutions are not closed, okay, but under proper subgroups of it. Okay, fine. So, for example, the set of solutions of special relativity is closed under the Lorentz transformations, and the set of solutions of Newtonian gravitation is closed under the Galilean group. What makes general relativity special is that the invariance group of the fields that satisfy the Einstein equation is the diffeomorphism group, so the solutions of general relativity are closed under arbitrary coordinate transformations. This is why general covariance seems essential to general relativity, but not to Newtonian gravity, special relativistic mechanics, or classical electrodynamics. Being generally covariant is perhaps necessary, but is definitely not sufficient for this general invariance. There must also be no absolute or prior geometric elements independent of matter sources. If this is somehow necessary and sufficient for general invariance, and hence to capture what is special about general relativity, is difficult to make rigorous. Note, in the philosophical literature, it is standardly assumed that two models, the MGT and M prime G prime D prime, are isomorphic if and only if their underlying manifolds are isomorphic, and for some diffeomorphism, the H G prime equals H star G blah blah blah. In the case where M equals M prime, the diffeomorphism H can be thought of as only being applied to G and T and not to the points of M. This is important in what follows. The next section explains the whole argument as is usually formulated. Okay, so you're applying the change not to the model in some sense. You're applying it to like the parts of it, because the model, if it's invariant, all the models can be shifted between each other, so the model doesn't really matter. It's sort of like the conditions that the model you're plugging into the model. Okay, this is way over my head, really. That's cool. Given some model of general relativity, MGT, Any diffeomorphism H that maps M to itself can be extended to a transformation on the model giving M H star G H star T, which is also an empirically equivalent model. In particular, for any A alpha B beta and A alpha bar and B beta bar representing two particular spacetime events in the two models, this equation-y thing where you've got G alpha beta, A alpha B beta is equal to G star of H star of all the things. You distribute H star over everything, I guess. So yeah, and the H star is just your transformation. This had better be so because these expressions compute in their respective coordinate systems to give the spatiotemporal distance between events which is an observable and should be for the same for all observers if the local light cone structure is to be fully invariant. Consider some model MGT and apply a diffeomorphism that is the identity everywhere outside some region called the whole, and not the identity inside the whole. The result must also be a model of the field equations. Consider a point P, element of the model, inside the whole. In the new model, in general, P has different values of the fields than does in the old model. Hence, for example, the world line of some galaxy going through the hole may pass through P in one model but not the other. So the whole argument here is basically you've got some like weird spot outside of the rest of physics, and that's the whole. And so it's you've got like identity everywhere. It's like you've got this two models and everything's the same, except the whole is some sort of dead spot where wherever everything else lines up, that spot it doesn't line up. Okay, so if we regard the points M as representing the points of space-time, so the two models represent observationally equivalent but different possible worlds, then we have a failure of determinism if some of the past state of the galaxy lies outside the whole, because this past state does not determine whether the galaxy passes through P or not. Einstein initially took this to mean we can not have a generally covariant theory. Yeah, if you have holes, then you can't have, like, everything isn't gonna match up, so the covariance falls apart. Okay, so MGT and MGT prime are standardly defined to be Leibniz equivalent if and only G prime equals H star prime and T prime equals H star prime for some diffeomorphism H. So they are Leibniz equivalent and only if they are isomorphic in the sense of the definition at the end of the previous section. The relationalist takes Leibniz equivalent models to represent the same world, so the whole argument is not a problem for them. If they only are relational, if everything's already relational, then the whole it just falls, it collapses. Okay, because the relation is what's real. According to Ermina and Norton, however, the substantivalist must think that Leibniz equivalent models can, in general, represent different worlds. This is because they take the substantivalist to be committed to the manifold substantivalism, according to which the points of the manifold M represent spacetime points, and the particular spacetime points represented by particular points of the manifold do not vary between the models above. See, the relationalist says the stuff only exists insofar there's a relation between two different points. Like, these 2 points line up with these 2 points, and if there's a relation there, then it's real. But if there's a hole in one of them, then there's no relation anyway, so that's not real. But the substantivalists think the points are real, so that means there's a hole in the area of points, and there's different points there. Now, this is where last time I thought about this, I might have been 19, which is a scary long time ago for me. Actually, it's a little weird. But like I was like, well, what do you mean by a substantive point? Aren't you guys mathematicians? Like, I didn't know that points had substance or like space. Like, that freaked me out. I said I didn't voice my opinion at the time. I still feel bad about that. I was confused about it. It was like, why are you saying weird things? Anywho, I was talking to a very good philosopher of science too at that time. Forget what was that guy's name. Very, very good. In particular, Ehrman and Norton assume that if P is an element, the M represents some spacetime point in E. In the context of one model, the same point must represent the same spacetime point in any other model built on M. However, it is possible to deny that the same P represents different spacetime points in different models while still maintaining substantivalism in the sense that spacetime is taken to exist independently of matter. There are various versions of sophisticated substantivalism. For example, according to metric field substantivalism, spacetime points are represented by combinations of M and G, and the points of the bare manifold do not represent spacetime points at all. Okay, that's interesting. I'd have to read up on that. Keeping track of which elements of the model represent which spacetime points in different models is easier if the representation relation is thought of as a function from mathematics to physical events or spacetime points. The domain of the function could be the manifold M, as with manifold substantivalism. Then, one form of sophisticated substantivalism is just the denial that the representation function is the same in different models. Alternatively, the domain could be defined to be the collection of all tuples Mg, which gives metric field substantivalism, according to which only the manifolds and metric together represent space-time. What the whole argument shows depends on what is assumed about how space-time is represented by models of general relativity. The putative indeterminism that is supposed to follow from substantivalism is only an issue if points of the manifold represent spacetime's points independently of the rest of the model. Philosophical debate about the whole argument aside, in scientific practice it is standardly supposed that Leibniz equivalent models of general relativity all represent the same physical world. The gravitational field can then be defined as an equivalence class of models. Diffeomorphisms are the isomorphisms in the category of differential manifolds, and arguably manifolds are only given up to diffeomorphism, and hence we might regard being related by a diffeomorphism as an identity criterion for manifolds. However, it does not follow that being related by diffeomorphism is an identity criterion for models of a given theory, because the assumption that diffeomorphism is the equivalence relation on models is a feature of general relativity, not pure mathematics. In the next section, the idea that hot helps with the whole argument is introduced. Okie dokie, let's see what that has to do with anything. Homotopy type theory to the rescue. Hot, as explained below, includes the univalence axiom, which says very roughly that equivalence is equivalent to identity. Why would equivalence be equivalent to identity? I mean, depend if you're just saying identity is identity, that doesn't make sense. Well, it makes a little too much sense, kind of trivial, but whatever. If diffeomorphism is taken to be the equivalence relation on models, under univalence, all models related by diffeomorphism are identified. Hence, it might be argued that models in the whole argument related by the whole diffeomorphism necessarily represent the same possible world. The rest of this paper considers how this kind of argument might be made vigorous, and more generally how the difference between intentional type theory and set theory relates to the conceptual and philosophical issues concerning how models in general relativity represent space-time. I mean, if you're just gonna, I don't know what this univalence is. Apparently everything hangs on that. But I mean, I don't, univalence axiom, equivalence is equivalent to identity. I mean, I could be equivalent in height to somebody, but that doesn't make us the same person. I mean, I don't really know what equivalence means on this then. Okay. Michael Schulman argues that what is wrong with the whole argument is that the diffeomorphism H that witnesses the isometry of the two models is not the one that is used to compare points in the two models, the latter being just the identity map between the manifold and itself. According to him, the apparent indeterminism and paradox of the whole argument only arise because the whole diffeomorphism H is used to generate a map H star that is applied to the metric, while H is not applied to the manifold itself to generate the new model. Thinking in terms of set theory, which is extensional, is not relevant whether H is applied to both because the model is just the collection of manifold, and the fields of which is thought of as an independent entity, and M is mapped to itself by H. It is explained in what follows why hot does not facilitate this way of constructing a model of general relativity. It turns out that univalence axiom is not crucial. Rather, everything depends on models of general relativity being taken to be dependent types and how they differ from the Cartesian product used in set theory. According to Eric Curiel, when one applies diffeomorphism, one must apply it to both the manifold and the metric. No other procedure has physical content. If he is right, then hot is a natural way to incorporate that constraint, and so to avoid the whole argument altogether. Okay, so if you're using a metric that does not permit the whole argument, then the whole argument can't get off the ground. Okay. Hot is a dependent type theory that can be interpreted in homotopy theory, but can also be understood without it. The basic components of the framework are types and tokens of types, sometimes terms or elements. For example, there is a type n, the natural numbers, whose tokens are individual natural numbers. For example, 5 or 24, and so on. So 5 is a term, so these are terms 5 and types n of the natural numbers. Okay. Types and tokens. Okay. Whatever. So wait, what am I saying? 5 is a token of the type natural number. That makes way more sense. There are also types corresponding to propositions. The tokens of these types are called certificates to the truth of the proposition, roughly proofs, also called witnesses. Okay, so you got a witness, or certifier. A proposition may have multiple certificates. Some types can be read in both ways. For example, iso AB can be interpreted as both the proposition expressed by A and B are isomorphic, and the type of isomorphisms between A and B. Logical operations such as conjunction, disjunction, and implication correspond to the type constructions product, coproduct, and function types respectively, and quantification is achieved by using dependent types. Thus, Hot incorporates constructive logic into the framework rather than being built on top of a subset logic. I don't know about that. I mean, you can build it in, or you can make it up. This is sort of a question about exactly what do you mean by incorporated versus built on top of. I mean, it had to be set up in a certain way, but I don't think anything's critical there. Hot is intentional. The precise sense of this is explained in the next subsection, but it also relates to the fact that types are individuated by their definitions, not their extensions. So, for example, the 0 type is a special type that is defined to have no tokens, though there may be other types that are also empty. Okay, that's interesting. Something having a property, for example, a number being prime, is expressed in the theory by a dependent pair consisting of the thing and a certificate to the proposition that says it has that property. Hence, subtypes are more complex than their types, unlike subsets that are restrictions on their sets. For example, there is a type of prime number p whose tokens are paired, such as 5p5 isn't. So the token 5p5 element of the numbers p, and 7p17 where p element of the type p, where pn is a certificate to the fact that the number is prime. In Hot and in general, a Lorentzian manifold is not just a manifold M that can be equipped with a Lorentzian metric, g, a function from pairs of points of the manifold to real numbers, but rather a pair consisting of a manifold and a Lorentzian metric defined on it. In Hot, but not in general, this is a dependent pair Mg. The significance of this is explained in the following subsections. A lot of stuff to keep in your head here. Hot has two different identity relations. External identity x triple bar y says about the language x and y are two synonymous expressions, so it's not a statement in the language of Hot. And internal identity x equals y is a proposition expressed by the language and represented by the type IDA xy in the theory. External identical elements may be substituted for one another in any context with no restriction. Internal identity is not so simple, but this is the source of the interest and power of Hot. Okay, so it's a proposition expressed by the language represented by a type. So identity A of xy. Tokens of the type identity A xy are called identifications between tokens x and y of type A. In homotopy interpretation, these are represented as paths between points x and y. As explained below, the properties of tokens can be transported along paths, meaning that tokens of propositions can be constructed to implement the law of the indiscernibility of identicals, and that any property of x is also a property of y, and vice versa. All functions respect the internal identity, that is, x equals y, f of x equals f of y. Nothing we can express within the language of Hot can distinguish the tokens that are internally identified. This means that the univalence axiom can be consistently added to the basic framework of Hot. Okay. Well, it can be added, yes, in terms of this identity function. It says that the equivalence type of two types is itself equivalent to the identity of those two types. Yeah. For present purposes, what matters is the consequence of this, that two types being equivalent entails that they can be identified. So is there an existence or a witnessing of this somehow built in? Maybe that's what it's going on here. You're getting a witness function, or the what are they calling it? The certificate. You're getting a existential certificate built in with this identification, this internal identification, and since the certificate has to probably work with the diffeomorphisms, that is what you're getting that will prevent the whole from causing a problem. Okay, that makes some sense. You're just building it, but I mean, again, this is a nice system, but it seems like you're building it this way to be convenient, which is okay. Importantly, internal identity does not imply external identity because it does not allow for substitution in all contexts. This is the formal sense in which the theory is intentional. Thus, hot identifying two tokens of the same type does not collapse them together because their identity type may itself have structure. Since IDA XY is a type, it may have multiple tokens, of each of which is an identification of X and Y. So they may sometimes be thought of as multiple proofs that X and Y are different certificates, I guess. Yeah. Every token of every type is trivially identical to itself, but also non-trivial identifications are allowed between any tokens of a type, including higher identity types. Under univalence, non-trivial automorphins produce non-trivial identifications. This is an expression of the familiar idea of a non-trivial automorphism as a map from a structure to itself that is not just the identity map. The non-trivial automorphisms of differentiable manifolds are diffeomorphisms, and so hot with univalence. So in hot with univalence, they correspond to non-trivial identifications of manifolds with themselves. Yeah, so you've got these certificates built in as diffeomorphisms, in some sense. Okay. Products and dependent pairs. Given any two types, A and B, we can form the product A cross B, the tokens of which are ordered pairs, small a, small b, small a and b, as a token of the type A cross B, where A is type of A and B is type B, token of B. This is one of the basic constructions in hot, not derivative as in ZFC set theory, where ordered pairs are sets of a certain form. Identity for products is component-wise, so that A comma B is equal to A prime B prime if and only if A prime and B equals B prime. Hot is a dependent type theory in the sense that it allows definitions of types that depend upon tokens of other types. The family of types PA is indexed by a token of some other type capital A. For example, token X of type A given type P of X is token Y of A gives type PY, and so on. Given a family of types PA indexed over A, there is the dependent pair big sigma small AA P of A. So what is this, the quantifier were they saying? I forget. Tokens of sigma AA PA are dependent pairs XP whose first component is a token, X element of A, or X is a token of type A, whose second component is a token P of the corresponding P of X. P can be thought of as a predicate on tokens of A. The type P of X corresponds to the proposition that X has property P. Okay. A token P of X is a certificate to this proposition. So the token P of X is the certificate to this proposition. Thus, the dependent pairs of type sigma AA PA may be regarded constructively as the type of all tokens of A having property P. Yeah. So they built up this thing of all the, see, is the quantifier, all tokens of A. Okay, so you built this up, but with a certificate here. So in some sense, it looks like you're building in the proof of it, certificate to the proposition, some sort of existential, in my opinion, or I don't know. This is a little complicated for me. But again, the work of the certificate is what's I think the certificate's what's doing the work here. So we'll see where this is going. Given an identification I between tokens in the base type, we get a transport function, tau I, px to py. Thus, given a certain certificate that x has property p and an identification between x and y, we can produce a certificate that y has property p. So the certificate is transitive, I guess. You can, if x, then y. The identity criterion for dependent pairs is different from that. The identity criterion for dependent pairs is different from that for products. Given two dependent pairs xp and yq, the identification between them consists in an identification I, ID xy, and an identification j. So this is IDA and this is ID py, tau pq. Alright, that's fine. Recall that to identify products A, B equals to A prime, B prime, we must have the corresponding identities A equals A prime and B equals B prime of the components. Dependent pairs may be identified even when there is no identity between the second components. In this case, P cannot be identified with Q because they belong to different types. Rather, it is tau I, P, that the transport of P along the identification I between X and Y that is identified with Q. Okay, so you can, depending on what you're doing, you can get it all to work together. It's a nice picture, I guess. Univalence. Univalence is an axiom that can be added to the basic rules of the type theory. Its exact form is a matter of some subtlety, but it has the consequence that any two equivalent types can be identified. Okay, I mean equivalence and identity, but I mean in some sense, what is the equivalence then? Okay, types A and B are isomorphic if and only if there is a function f from A to B and g from B to A such that g of f of A equals A for every A in A, f of g of B equals B for every B in B. So you're transposing the g and f functions. Yeah, so that's isomorphism for all things, tokens of type A. Equivalence is another relation between types that is similar to isomorphism, and for the present discussion, the difference between them does not matter because any equivalence is an isomorphism and vice versa. Okay, so you've got some sort of isomorphism. Given any identification between types, we can immediately construct an equivalence between them. Thus, there's a function identity AB implies there's an equivalence AB. The univalence axiom entails that there is an inverse function to this. Equivalence AB implies ID AB. Hot and the whole argument. Consider the type of man manifolds and the dependent pair of sigma token n of man Lorentzian n of manifolds equipped with Lorentzian metrics. Tokens of this type are dependent pairs. Mg diffeomorphisms between manifolds is an equivalence relation. So again, I think they're defining their diffeomorphism as equivalence. Maybe that's a little bit begging the question. I mean, maybe not. I don't know enough, but it just seems like they set it up so that this is exactly where they were going. Like this whole, like they wanted to get this way, and so they set it up this way, and this is how they're getting out of the whole argument because they set up a diffeomorphism to be the equivalence relation in the hot thing. Okay, which is okay. I mean, it might be right. It seems like they knew what they were doing when they wrote this paper, which I'm sure they did. Thus, under univalence, every diffeomorphism H from M to itself produces a self-identification of M. The transport function takes any self-identification H of M equals M and gives a mapping from metric G onto M to a metric H star G on M. That is, the construction of isometries from diffeomorphisms is taken care of automatically by transport. Yeah, they define that so that you can just get this stuff out nice, which is convenient. By the identity criterion for dependent pair types above, a non-trivial diffeomorphism H of M equals M gives a corresponding identity MG M H star G, where M is identified with self via H and H star G is trivially identified with itself. On the other hand, if M is mapped to itself by the identity diffeomorphism, which is to say trivially, then there is only an identification between the dependent pairs M G and M H star G if G equals H star G, which is not true for general diffeomorphisms H. This distinction is made visible in hot, which allows us to express non-trivial self-identity of M. Yeah, so if you're doing something funky with how you identify yourself, the self-identity won't be trivially like it won't obviously line up. But it may line up, but you have to have a theory of that. Okay. This non-trivial identity of M. Schulman's objection opposite may be paraphrased by saying that one should not apply I to M and phi to G. This cannot be done with dependent pairs. However, the fact that a model is taken to be a dependent pair has nothing to do with univalence. Furthermore, it can be stipulated that the representation function respect to equivalence, in this case diffeomorphism, without univalence. This is just what Leibniz equivalence says about diffeomorphic models. Hott enforces this only under the assumption that Mg is a dependent pair, so univalence alone is not sufficient. The assumption that Mg is a dependent pair is sufficient if it is supposed that diffeomorphism is identity for models, so univalence is not necessary. But univalence enforces this in that the representation function respects equivalence. Okay. It might be possible within Hott to perform the whole model of general relativity as a product rather than a dependent pair, by first forming the dependent pair, acting on it with H, and then projecting out the metric and any other fields and adding them to into a product with the manifold. However, this would be a very artificial and unmotivated way to proceed counter to standard practice, and all notions of equivalence and identity for such products would have to be defined component-wise via the relevant definitions for dependent types. Okay, yeah, so depending on how you set it up, they're saying if you set it up differently, it would be an unnatural way to set it up. I don't know what the value of that argument actually is. It seems, I don't know. Yeah, that's a little over my head, the difference between a product rather than a dependent pair. But maybe it matters, because, I mean, like I said, the certificate is what's doing the work here. It's what's guaranteeing that you have this sort of a witness that these things are equivalent, and that's what's doing the work in the identity functions. And so I'd have to understand more about that. Okay, that's fine. Conclusion. The individuation of the metric G in a model of spacetime is a subtle matter. Suppose it is specified to be the Lorentz metric. The definite article does not pick out a metric in the sense of a function from points to the real numbers, but rather the form of such a function. Any such actual function must be defined on a particular manifold. Type theory enforces clarity about such matters. It is implicitly assumed in ordinary mathematical practice that Mg is a dependent pair, since equivalence of Lorentz manifold is isometry generated by diffeomorphism on M, but Hott enforces this. Okay, again, they're reinforcing their position that this is sort of the way things are done, and this theory does that sort of thing. If the type of Lorentzian manifold, Lor M, is a dependent pair, it is natural to take a model of the field equations of general relativity to be a dependent tuple. Accordingly, the definition of equivalence should be that for a dependent tuple requiring that to generate a diffeomorphic model, the same diffeomorphism is applied to M as that applied to the metric and other fields defined on M, and so not allowing the formulation of the whole argument. Yeah, so it forces via all of that stuff above the diffeomorphism throughout M. So the whole doesn't exist if you can't make space for it, because the diffeomorphism is enforced throughout the whole thing. Nothing but the type theory or univalence requires a generally covariant representation. However, the mathematics of manifolds is built for it, and dependent pairs in type theory can enforce it. The diffeomorphisms of a differential manifold automatically generate the pull back and push forward of any fields defined on it, and the equivalence between dependent tuples of manifolds and fields is determined by the underlying equivalence between manifolds, that is by the diffeomorphism group. Under univalence, this implies that the models in the whole argument are identical. However, even this is compatible with stipulating that they represent different possible worlds if representation is not required to respect identity. Furthermore, type theory can be used to represent the mathematics of a preferred coordinate system, and so to model physics in a generally non-covariant way if required. The example of the whole argument suggests that HOT may provide a good framework for tackling foundational problems in physics, for example, concerning the interpretation of gauge fields, concerning what and how mathematical structures should be taken to represent physical structures. Being a type theory, HOT requires precision about how everything is defined, and being in an intentional theory allows symmetries to be represented as non-trivial identities, respecting the fact that they map a structure to itself while also keeping track how they do so. Okay, cool. Haven't done any philosophy of physics before in this thing. I'm a little worried about this whole what I was talking about here. It's just they're reading the theory off the practices and then saying this HOT enforces the structure of the theory, but that might be exactly begging the question of how the theory should be set up to begin with. But chances are I have no idea what I'm talking about, and this is entirely reasonable in this area. So I just don't know. Creative Commons. Hey, well, this might be my one and only time of being completely legal, because I give all credit to the authors here. Yes. Okay, so that was fun. Maybe I'll do some more, I'd love to do some philosophy of biology one day. I should do that, look into that. Philosophy of physics is fantastic. Also, everyone should read some philosophy of physics, philosophy of science, philosophy of biology, things I've spent a bunch of time thinking about. Not recently, but I have spent some time thinking about this stuff in the past. Okay, cool. So I hope everyone has a wonderful night. Stay safe, stay healthy, everyone. And I'll see you, not tomorrow, I'm taking Mondays off, I think, so I'll be back on Tuesday.